Hi students, now we'll talk about some examples about projectile motion. Some examples and projectile motion from a cliff or full projectile motion as we see here from an origin point, and we have the all curve as a parabola. Maybe also we have like this. We can change the angle of the projectile. Then we have different shapes of projectile motion. Also sometimes we have this shape of examples. We have a gun with a projectile motion for the bullet and another falling body. We have two trajectories, the free falling body trajectory and the projectile motion trajectory. We need to make an equal between these two trajectories and find which angle, for example, or which velocity or at what time we can hit the target. All of these examples are use the same principles, which are the position and velocity vectors. Let us now look at this example, starting with this. If we look at this gun or cannon, we have a projectile. The X motion is constant. We can see the different places, the different horizontal places for the projectile are the same distance, have the same distance. This means there is no change on horizontal velocity or speed, which is in X direction. Look at the trajectory of the vertical speed. We have different or increasing in the places of each time. This means we have acceleration because each time we have more distant or past distance. Okay, this is just a note. Now we have this example. By the way, we have 6 pages to solve this example, but I solve it in details. Because of that, I spent 6 pages. We have during Independence Day calibrations. A cannonball is fired from cannon on a cliff toward water. The cliff height is 100 feet. The velocity V0 is 600 feet per second, and the angle is 30 degrees above the horizontal. It is 30 degrees. So we have the givens is the velocity, initial velocity. We have the angle, we have the height. We need to compute some things. We need to find the maximum height of the cannonball. The maximum height is at this point, as we see. We can compute it from our origin, which is the cliff edge. We can find this height, or we can find all the height. We just need to add h to it. Also, we need how long it will take to reach the final point. We need to compute the total time, the flying time. Also, we need to compute x, which is the range. This is sea level. So we need to start solving our problem by some systematic steps. If we look at page number 77, we will see in the purple square there is a strategy to solve projectile motion? At the first, we need to define our coordinates. I will take the origin at the edge. I will take this as an origin. Okay, so this is x positive, this is y positive, this is y negative, this is x negative. I have this positive x and downward is negative y. So next, I need to clarify the known quantities. The known quantities is phi naught, which is 600 feet per second, alpha naught, which is the angle, h, which is the height, which is 100 feet. What is the unknown quantities? The flying time, all the flying time, the maximum height, the range from this origin to the final point. Okay, we need to understand the sentences and the words here, and I think the sketch can explain that to us better. We need also to find the samples. What is the formulas? We will see that. We will use, as we said before, the position vector and the velocity vector. Then we need to execute and put the known parameters in their places in our formulas. So we need now to start with position vector and velocity vector as we found them before. We have just two coordinates, x and y. X to the right, y to the above direction. We will not use z direction. We have motion in 2 dimensions. So the position vector is has x component and y component. Also the velocity vector has x component and y component. And these components come from equations of motion. We know them. Then we need to evaluate. We need to find the results or the unknowns. In our example, we need to be careful that we have V naught 600 feet. We need it in meters. And alpha is 30 degree. It's okay. And h, which is the height of our origin above the sea level, is 100. So the height of the sea level is minus 100 feet. And the reference is the edge of that cliff. This is the second sheet. Now we need to find our velocity in meters per second. Our velocity is 600. This is in details. Feet per second. But I need to multiply it by the conversion coefficient, which is 1 over 3.28. Every 1 meter is equal to 3.28 feet. I need the feet in the denominator to cancel it with the original unit. So the velocity will be 600. The seconds are the seconds. We have still the meter. And 600 is multiplied by 1 over 3.28 will be equal to 182.88 meters per second. We can approximate it, but in general I didn't approximate it. Yes. And the height, which is 100 meters, or the depth of the height of sea, which is negative 100, but I said there h is positive. It's okay. In feet, I need to convert it in meters. It will be 30.48 meters. Maybe you can approximate it to 30.5. Okay, A. We need to find the maximum height. At the maximum height, at this point, the velocity at this point, the vertical velocity will be equal to 0 because it is a retaining point. The velocity, vertical velocity means Vy is equal to 0. Okay, from where can I bring Vy? From the velocity vector. This is Vy. This is Vx. This is Vy. I should put it equal to 0. This is Vy. V naught sine alpha minus gt is equal to 0. V naught is known. Alpha is known. G is known. I have unknown t. Then I can find t at the highest point. I need just to order the equation, the formula. Then t will be equal to v naught over g sine alpha. This is at maximum height. Okay, what else? I can find t. Just put v naught g sine 30. It will be 9.3 seconds. Okay, this is my trajectory. My projectile takes time t to go up. This is going up or rising time. It is 9.3 seconds. Now we know the time to be at y max. We can apply this in the position vector. What is the position vector? As we see, this is the position vector. I can put the time in x component or in y component. If I put t going up in the y component, then I will find y going up or y maximum. I will use y component in the position vector. From the position vector, this is the position vector again. This is ry or the height. This relation. So if we compute the height, we need to use the time going up at the maximum height. So just I need to put t in t. If I use that, v naught is known, alpha is known, this is t, g is known. Just I need to find the numbers, then the maximum height above the reference. This is the velocity vector from the reference. It is 426.3 meters from the cliff. But from the sea level, I just need to add h. This is h. So it's 456.78 meters above the sea level. Is that clear? This is the first requirement, A. B. What is the time that's required to go all the path? Or the flying time, all the time. I can compute it at the final point using the vector position again. I know where's the vector position. This is the vector position. I know the coordinate of phi at the final point. It is -100 feet. Y is equal to -100 feet below my reference point. So I know Ry or Y position, vertical position. So I can use the Y component from the position vector, which is equal to V naught T sine alpha naught minus half gt squared, which is equal to -h, -30.48. This will allow me to find the time. I have the second power relation in square the time. I need just to reorder this relation and put theta equal 30, V naught equal to 182 and something, Then I have my final relation is equal to t squared minus 18.65 t minus 6.22 is equal to 0. I will use the general formula to find t. T is equal to negative b plus minus b squared minus 4ac over 2a. b, this is a, which is 1. This is b, which is negative 18.65. c is equal to negative 6.22. I just put them in this relation, and we have plus negative. We have two values, so we have two mathematical values, but just one accepted physics value. We have two values for the time at that point, which is equal to 19 seconds or negative 0.33 third a second. This is, we cannot accept this value. We can accept this. So the total time is 19 seconds. What about this value? This value, if we draw the rest of our trajectory, the time mathematically from here to here is negative 0.33, or the time from here to here. We can, but there is no motion in this place, so we can't take this value of time. This is the second requirement. We have the final one, which is short one. We need to find the range. The range is simple. The range is from the reference point to the end point. This is the reference, x equal to 0, to the final point. We have the time. We have the velocity. In x direction, it's constant. So from position vector, we have the x component, which is rx, equal to v naught multiplied by t by cosine alpha naught. We have v naught, we have t, the flying time, we have alpha naught, which is equal to 30. The range will be is equal to 1 kilometer, 737 meter, 0.36, all in meter unit. So this is the range. I solve this example in details and make it long, but repeat it many times, it will be more simple. Thank you.